Okay, so what's up, guys? So this is another lesson about kinematics, which is the two dimension and the three dimension. Okay, so let's discuss what is two dimension and three dimensional motion. Okay, so two and three dimensional motion are normally seen as curves, circular motion, and parabolic. So we know that those three deals with not just a straight line. It is viewed uh, as a motion that are has curves in their path. Okay, so however, two and three dimensional motion cannot be used to describe motion in one dimension. So when we talk about uh, the two and three dimension, they cannot be seen as one dimension. So for the reason that one dimensional motion is a motion that can be associated as a linear motion. Okay, so two and three dimensional motion are also known as can be seen as a projectile motion. So projectile motion are motions that has a curved path from the starting position until the final position. So this curve path is what we call the trajectory. So normally those trajectories, example of those are the pathway of the basketball when shot from a distance, or even in a short range. It can be seen as curve path. Okay, so from the spike of the volleyball or a toss, cliff jumping or diving, the pathway of the person, you will see that there is a curve in their path. Okay, so this is the example of a trajectory. So as you can see, those blue line, this one. So yeah, this blue line is what we call the trajectory. So this is what the cannon has fired. This is a shell, and this blue line is its path until it reaches this position. Okay, so that is our example of projectile motion. So we will be dealing more of it. Okay, so we will be dealing more of this projectile motion in this lesson. Okay, so two dimension motion, we're dealing only with x and the y axis. Okay, so that is what the two-dimensional motion is. Okay, so we're dealing only with the x axis and the y axis. Okay, so but when we talk about the three-dimensional motion, it can be seen from three axes. So z, x, and y. So there is an additional axis, which is the z-axis. Okay, so the two-dimensional motion can be only seen up front, only seen in front view. Okay, but when we talk about the three-dimensional motion, either way, it can be front view, top view, and side view. You can see the path of the object. Okay, you can see the path of the object that it has a movement. Okay, so from front view, you can see here from this drawing's perspective that front view, we have the red box. When you go on to the side, you can see the side view, which is the green side, and when you go up, you can clearly view the blue side of the blue side of this perspective. Okay, so that is our uh, three-dimensional motion. So that's the difference between the two. We have an additional axis, which is the z-axis, and the x and y axis, or the two-dimensional motion, can only be seen in one perspective. Okay, so we have a formula here in our two and three dimensional motion, which is not new. This is we have discussed this in our previous lesson. We have d is equals to vit plus 1 half at squared, which is this for stands for distance. Vi is our initial velocity, a is acceleration, and t is time. So let's try to solve this one. A tourist tries to experience the Kawasan Falls dive. He did a running start before jumping into the water with a speed of 3.5 meters per second, and it took for the tourist 2.8 seconds to land on the water. Solve for the height of the falls and the distance away from the falls he earned from jumping. So, okay. Using the formula of d is equals to vit plus 1 half at squared, we can solve for this for our uh, distance and the height. Okay, so this is the representation. So the tourist runs for 3.5 meters per second, and we will be computing the distance from here to here and also the height from here down here. Okay, so that is what we're going to solve. Okay, the height and the distance. Okay, so these are the two components that we're going to solve. Okay, so yeah. Okay, so for this, for the terminologies, the distance between the landing point and the starting point is what we call the range. Okay, and the height is what we call y max or height, or simply basically height. Okay, so these are the terminology, so don't be confused when you encounter this in our future problems. Okay, so y max is the term for getting the height on which the object will fall, and the range is the distance of the object from the base of the distance, uh, the base of the distance it falls into. Okay, so using this formula, d is equals to vit plus 1 half at squared, we can substitute, or we can solve for the range using vit. Direct substitution, 3.5 multiplied to 2.8 seconds. Let's try to solve it. 3.5 times 2.3.5. Wait. Yeah, okay. 3.5 times 2.8. Okay, so the answer will be 9.8. Is it 9.8? Yes, 9.8 meters. Okay, so for the y max, using the formula of 1 half at squared, y max, direct substitution of 1 half times 9.8, 1 half, 1 half times 9.8 for the gravity, and 2.8 seconds square, we will arrive at the answer of 38.416 seconds, or 38.42 meters. Okay, so that is our answers for the range and for the y max. Okay, so proceeding for the solution. So it is a direct substitution, so using the velocity and the time, so we can solve for the range. And for the y max, for a higher ground, it falls down freely, free falling. So that's why the acceleration that we use was the gravity. Okay, so since it is based on the earth, that's why we use the gravitational acceleration of the earth, which is 9.8. Okay, so for the first example, we just solve for half of the full motion, full length, and full height. So we have another projectile motion, which is seen in our uh, in our title page, in our title screen a while ago, that there is a full length from the starting point of the bullet shell up until to its last part. That is the full range motion. Okay. So here is the example. Start from here all the way in this position. So here is what we call the full range motion. Okay. So we have here the Y max in the middle, because every time the object travels, when it reach its peak, it is always in the middle. That is that is the position of Y max in our trajectory. Okay. So when we zoom out in here, we can see that there are two components of our initial velocity. So since it is in uh, an angle position, so since it is in an angle position, it clearly has a y-axis and a y component. Y component and x component. So we have two components for our uh, initial velocity. So we all know this previous on our previous lessons, that there is a x and y component whenever an object has an angled vector. Okay, so projectile motion are the motion that are almost same as the ones that fall from the top of the high place or location. It has a y max, range, and initial velocity. So all those three are present in our trajectories. So the initial velocity is a resultant. Yes, this is what I'm saying a while ago. It is a resultant of our vertical and the horizontal velocities. And but what we're just seeing is the initial velocity, or the resultant of the x and the y velocities. Okay, so another point here is when the object reaches its peak or the y max, the velocity becomes zero. Meaning whenever the object traveled from its starting point until it reaches the top, the velocity gradually becomes zero from the starting point up until its peak. Okay, so when it reaches the peak, it stops moving, or it stops accelerating, or it stops its velocity. From starting point, it starts from here having its initial velocity. When it reaches its peak, the velocity becomes zero, and the momentum brings the object down. Okay, so the momentum build up from the starting position up until its peak is what the object is using for it to reach the other end. Okay, so as it reaches the top, the velocity becomes zero. Y max is the peak height on which the object attained as it courses through the full range, and also Y max is located in the middle of the range. So we all know this because we've just seen it from our drone. Okay, so let's have the formula of the range. We have the formula of the range, which is R is equals to VI squared sine 2 theta all over G. And the Y max is VI sine theta, parenthesis for the VI for the initial velocity, and the sine theta, it is squared all over 2G. So the formula shown are the ones to be used in solving problems of the range and the y-max. Both formula rely on the gravity, since both motion stays up in the air until it reaches the end point of the range. Okay, so y-max and range relies on gravity, even though range is on computation of the y-axis. Even range is the computation of the y-axis. X-axis. Still, the motion path of it is up in the air. Okay, so up in the air, we have gravitational acceleration, uh, uh, that is embedded in our formula in the range. Okay, so automatically when we talk about y max or the height, gravity is still present. Okay, gravity will always be present. Okay, so not shown in the formula is the time. So time is not shown in our formula, and still it is also part of our component. Okay, so we have formula for time, which is the time to reach the maximum height, which is t is equals to vi sine theta all over gravity, and the total flight time. T is equivalent to 2 quantity vi sine theta all over g. So this 2 is just the multiplication or the addition of uh, two versions, or this is time to reach the max height plus time to reach the max height. That's why it is 2 total flight time. So for example, here we have the trajectory here, and the peak is here. So this is just the t, and this is another t. That's why t plus t is equivalent to our total flight time, total time of flight. So basically, this is the breakdown of the formula of total flight time. Okay, so that's why we just use these two to multiply 2vi sine theta all over g. Okay, so proceeding. So we have an example here. A soccer player kicks the ball with a velocity of 15 meters per second with an angle of 45 degrees to clear a 5-meter obstacle. Solve for the following. Time for the ball to reach its peak. So total time of flight, maximum height, vertical velocity, horizontal velocity, and total distance cleared by the ball. So total distance cleared by the ball. So let's try to solve. Uh, let's try to solve this one. So a soccer player kicks the ball with a velocity of 15 meters with an angle of 45 degrees to clear a 5-meter obstacle. So solve for the following. Just wait. Let's try to go a little. Uh-huh. Okay. So let's try this one. Wait, guys. Okay, so let's try to solve this one. Okay. Okay, so time's up. Okay, so time's up. So here is the answer, the computation. So solution for A, which is the time for that ball to reach its peak. So we have the formula of t is equals to vi sine theta all over g. Substituting the values or the formula for the formula 15 meters per second, sine 45 all over 9.8. Okay, so using this formula, we can solve for our time of the ball to reach its peak. Okay, so it is 15 sine 45 all over 9.8. So is our formula correct? So we have arrived at the answer of 1.08. 1.08, which can, yes, okay. So it is 1.08 seconds. And for B, solution for B, so using this formula 2, we just multiply this by 2 and we will arrive at the answer of 2.16. Okay, will it be 2.16? Yes, 2.16 seconds. Okay, so proceeding to number letter C, and for letter D, maximum height and vertical velocity. So maximum height and vertical velocity. So solving, please try to solve this one, guys. So timer's running now. Okay, please try to solve. Okay, so let's try to solve this one. So solution for C maximum height using the formula of y max is equivalent to vi sine theta parenthesis squared all over 2g. We will arrive at the answer of, yeah, wait. Okay, so let's try to solve this one. 15 sine 45 divided by 2, 9.8. So, whoa, wait. Okay. So, yun. So, guys, so this is a common problem that we forgot the square. Okay, so let's try to solve this one. We will arrive at the answer of 5.74. Is it, yes, is it 5.74? Definitely it is 5.74 meters. Okay, so solution for the which is the vertical velocity using Vy is equivalent to Vi sine theta. Substituting, we will arrive at the answer of 15 sine 45, which is 10.61. Will it be 10.61? Yes, it's 10.61. So we solve the vertical velocity, which is 10.61. Okay, so let's move on to the next, which is the horizontal velocity and the total distance cleared by the ball. Okay, so timer starts now. So guys, please try to solve this one. This is a practice on how to solve problems and how to use your calculator. Okay, that's why I'm showing you guys the proper calculator techniques and tips and tricks. Okay, so for this one, guys, so please try to solve this one. Okay, so please continue to solving. Okay. Okay, so so let's solve this last part. Okay, so solution for E for the horizontal velocity, it is Vx is equivalent to Vi cosine theta, 15 meters per second multiplied to cosine 45. We will arrive at the answer of, wait, danan, 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 danan. Then 10.6, will it be 10.61? Yes, it's the same, 10.61 meters per second. And lastly, for the total distance cleared by the ball, we have the range, which is R is equivalent to VI squared sine 2 theta all over G. Substituting the values of our range, we have here we have here 15 sine 2 multiplied to 45. Oh wait, but there is a square in our initial velocity. Initial velocity and all over 9.8. Okay, so let's try to solve for the range, which is 22.96. Will it be 22.96? Yes. So we solve for the three components, three sets of problems. So this is the last part, and yes, let's try to solve for another example. Okay, so a battleship fired a cannonball to the enemy ship. The known distance of the enemy ship from the battleship is 79.5 meters. So the cannon was fired at 30 degrees with a velocity of 30 meters per second. So, sir, what's the question? So, A, if the trajectory were to adjust to 60 degrees, will the battleship hit its target? And B, solve for the Ymax of 30 degrees and solve for the Ymax of 60 degrees. Okay, so let's try to solve this one. Okay, so guys, so please try to solve this one. This is nothing new. It is just the same as the previous lesson. It's the previous example. Okay, so please try to solve this one. Okay, so so let's try to solve for A. But before that, what will be the answer? Is it a yes or a no? Yes or a no? Well, the answer is yes. Okay, so sir, why? The distance of the battleship to the enemy ship is 79.5 meters. Okay, so solution for, oh, it's not F, it's A. So solution is our range is equivalent to VI squared sine 2 theta all over G. So substituting the values of this, we have 30 meters per second square and 60. So the answer is 79.5, which is a true hit. It's a hit from our uh, battleship. So that's why the answer is yes. So that's why the answer is yes, because the distance has reached the battleship reached the target, which is 79.5 meters too. Okay, so there you go. The answer is 79.5 meters. Okay, so for B, solution for B, that's B. Vi sine theta squared all over 2g. So substituting the values, okay, so Vi, which is 30 sine 30 square, okay, all over 2 9.8, which is 11.48. Okay, so 11.48. Yes, the Y max is 11.48. Y max for 30 degrees. Okay, and lastly for our letter C, so we have Y max VI sine theta. So we're just going to change our degree from 30 to 60, then the answer will be 34.44 meters. So so guys, this is our lesson for two dimensions and three-dimensional motion. I hope guys that I hope that you have uh, a wonderful time learning this. And if you have any questions, feel free to ask them. So I'm just going to let you guys question, and I'll be more than willing and more than happy to cater all those questions. So if you have questions, so feel free to ask them. Okay, so but I'm going to end this video, and if you don't have and if you have any questions, so the interview or the question starts right now. And I'm going to end this video. Thank you guys for watching. Thank you guys for bearing with me. So thank you guys, and see you, and God bless. Stay safe, guys. Stay safe. Stay safe.